Friends, I am Muskan from BSc Chemistry Honors final year. Today we are going to discuss pure vibrational and vibrational rotational spectrum of diatomic molecules, the IR spectra. Vibrational energy levels of a simple harmonic oscillator. A simple harmonic oscillator is the one in which the restoring force is proportional to displacement in accordance with Hooke's law. F is equal to minus kx, where k is called the force constant. For such an oscillator, the potential energy is given by half kx square. This is the equation for a parabola. Hence, a parabolic potential energy curve is obtained as shown in figure 3.21. Using the concept of quantum mechanics, it can be seen that if the vibratory motion of the nuclei of diatomic molecule is taken as equivalent to the simple harmonic oscillator, then the vibrational energy is given by the equation Ev is equal to V plus 1 by 2 h nu. Nu is the frequency of vibration and V is the vibrational quantum number with allowed values of 0, 1, 2, 3, etc. Putting mu is equal to C by lambda, that is equal to C into mu e bar. C is equal to omega e, where omega e and mu bar represent the equilibrium vibrational frequency in term of wave number and can be written as Ev is equal to V plus 1 by 2 hc omega e, where V is equal to 0, 1, 2, 3, 4. In equation 4, it can be seen that the vibrational energy level of a harmonic oscillator are equally spaced. They are shown diagrammatically in figure 3.23. For the lowest vibrational level, V is equal to 0, the energy of this level will be E naught is equal to half hc omega e. This is called 0 point energy. It implies that even at absolute zero, when all transitional and rotational motion cease in the crystal, the residual energy of the vibration E naught still remains, that is, vibrational motion still exists. Selection rule for the vibrational transition in simple harmonic oscillator. The gross selection rule for a molecular vibration is that electrical dipole moment must change when the atoms are displaced. Here note that the molecule need not have a permanent dipole. Based on this, the specific selection rule for vibrational transition is del V is equal to plus minus 1. Change in vibrational quantum number should be unity. The transition for which del V is equal to plus 1 corresponds to absorption, thus with del V is equal to minus 1 correspond to emission. Vibrational spectra of a simple harmonic oscillator. Applying the selection rule, as the transition can take place from between vibrational level whose vibrational quantum number differ by unity, the energy absorbed by a diatomic molecule taken it as a simple harmonic oscillator. When the transition takes place from V is equal to V plus 1 level will be given by del VE is equal to V plus 1 plus half hc omega e minus V plus half hc omega, that is equal to hc omega. Change in energy upon hc is equal to omega e, that is change in wave number is equal to omega e. Thus only one absorption line will be obtained in the rotational spectrum whose wave number is equal to equilibrium vibrational frequency of diatomic molecule. Otherwise too, as the vibrational levels are equally spaced, any transition from V to V plus 1 give rise to the same energy changes and hence only one absorption line is expected. Further, at room temperature, as most of the molecule are in ground state, ground vibrational level with V is equal to 0, therefore transition takes place are from V is equal to 0 to V is equal to 1. The frequency thus observed is called fundamental frequency and these spectra are observed in the IR region. Type of molecules showing vibrational spectra. As already mentioned, the gross selection rule for the diatomic molecule to give a vibrational spectrum is that dipole moment of the molecule must change when the atoms are displaced due to vibrational, so that it can set the electromagnetic field into oscillation. The condition required is only the change in dipole moment, possibly from zero, and molecule need not have a permanent dipole moment. For example, in case of homonuclear diatomic molecule like S2, O2, N2, etc., which has which have only stretching motion and vibration, no bonding motions and vibrations, the development the dipole moment does not change during vibration. Hence, these molecules do not give vibrational spectra, that is, they are said to be IR inactive. On the other hand, heteronuclear diatomic molecules like HCl, CO, NO, and polyatomic molecule like CO2, S2O, methane, ethane, these show change in dipole moment in some mode of vibration, give vibrational spectra, and said to be IR active. Vibrational energy level of an harmonic oscillator. When a molecule is undergoing simple harmonic oscillator, the restoring force of harmonic vibration is directly proportional to the displacement, and the energy of an harmonic oscillator is given by EV is equal to V plus half Hc omega E, where V is vibrational quantum number which may be 0 and integer. Omega is equilibrium frequency of vibration of the oscillator, that is for small displacement. Strictly speaking, the moment of an real oscillator is not perfectly harmonic. This is because as the displacement increases, the restoring force becomes weak, and for large enough amplitude of the vibration, the atoms of the molecules must fall apart. The molecule must dissociate it into atoms. Such a real oscillator is said to be an harmonic oscillator. P.M. Morse in 1929 suggested that the above equation has to be modified for an anharmonic oscillator by including one additional term as follows: V is equal to V plus half Hc omega E minus V plus half whole square Hc omega E Xe, where Xe is called the anharmonicity constant. Putting V is equal to 0, 1, 2, 3 in equation 1 and 2, the energy level of harmonic oscillator and anharmonic oscillators are obtained. It may be seen that the energy levels of anharmonic oscillator of a harmonic oscillator are equally spaced. Those of anharmonic oscillator are not equally spaced but fall more close together as the quantum number increases. Further, whereas the potential energy curve for harmonic oscillator is parabola, that of anharmonic oscillator is shown in figure 3.24. Selection rule for the vibrational transition of an anharmonic oscillator. Whereas the selection rule for the harmonic oscillator is change in V is equal to plus minus 1. Selection rule for the anharmonic oscillator is R, change in V is equal to plus minus 1, plus minus 2, plus minus 3, and so on. Thus, all type of vibrational transitions are possible. However, the transition from V is equal to 0 to V is equal to 1 is found to be most intense due to greater population of these energy levels, and it is called fundamental absorption. The transition from V is equal to 0 to V is equal to 2 has a weak intensity and is called first overtone. Transition from V is equal to 0 to V is equal to 3 has still weaker intensity and is called second overtone, and so on. Vibrational rotational spectra. Pure vibrational spectra are obtained only for liquids, whereas rotational motion is hindered due to interaction between the liquid molecule. However, in case of gaseous molecules, as the energy required for rotation is much less than that required for vibration, the vibrational motion is always accompanied by rotational motion, and hence we don't have a pure vibrational spectra. Instead, we have a vibrational rotational spectra lying in IR region. As rotational motion and vibrational motion takes place independent of each other. Applying Bohr open here approximation, the total energy of the molecule may be taken as the sum of rotational energy and the vibrational energy, which is much larger than the former. Thus, E total is equal to ER plus EB. It can be written as EBJ, EJ plus EB. Expressing in term of wave number, it can be written as mu E bar Vj, mu E bar J, mu bar V. But from equation 4, section 3.14, equation 2 and section 3.26, Bj bar mu Bj bar is equal to Bj J plus 1, mu bar V is equal to V plus half omega E minus V plus half whole square X omega E. Substituting these values in the equation 15, we get mu bar Vj is equal to Bj J plus 1 plus V plus half omega E minus V plus half whole square X omega E. Here mu bar Vj represents the wave number of rotational level with quantum number J in the vibration level with quantum number V. From equation 6, it is clear that the same vibrational levels so that V is equal to 0. There will be a number of rotational levels corresponding to J is equal to 0, 1, 2, 3. When a transition takes place from a level into quantum number V and J to a level with quantum number V dash and J dash, the energy changes expressed in terms of wave number will be given by del mu bar is equal to Bj dash into J plus dash plus V dash plus half का whole multiplied by omega E minus V dash plus half का whole square multiplied by X omega E. Bj into J plus 1 plus V plus half whole multiplied by omega E V plus half का whole square multiplied by X omega E. Restriction to the transition from V is equal to 0 to V dash is equal to 1. We get B J dash minus J plus J dash plus 1 plus 1 minus 2Xe whole multiplied by omega E. 1 minus 2Xe whole multiplied by omega E is equal to omega naught. It may be written, we can write del mu bar is equal to omega naught plus B J dash minus J plus J dash plus 1. For transition with J is equal to plus 1, that is J dash minus J is equal to plus 1, J dash is equal to J plus 1. Change in vibrational vibrational frequency in terms of wave number is equal to omega naught plus 2b J plus 1, where J is equal to 0, 1, 2, 3. For transition with del J is equal to minus 1, J dash minus J is equal to minus 1, that is J is equal to J dash plus 1. Then change in vibrational energy in term of wave number is equal to omega naught minus 2b J dash plus J. Combining equation 10th and 11th, we get change in energy in term of wave number is equal to omega naught plus 2bm, where m is equal to J plus 1. In equation 10, m is, and in equation 11, m is equal to minus J dash minus 1 in equation 11th. As J is equal to 0, 1, 2, 3, this means that in equation 12, m is equal to plus minus 1, plus minus 2, plus minus 3, plus sign for del J is equal to plus 1 and minus sign for del J is equal to minus 1. The nature of vibrational rotational spectra can be predicted from equation 12 as follows. As m naught cannot be equal to 0, therefore lines corresponding to the frequency omega naught will not appear in the spectrum. This wave number is called band center or band origin. As m is equal to plus minus 1, plus minus 2, plus minus 3 and so on, It follows that the spectrum will consist of equally spaced lines on each side of the band center, with spacing equal to 2b between any two adjacent lines. Keeping in view the selection rule del J is equal to plus minus 1, the absorption transition takes place from level V is equal to 0 to V is equal to 1, and corresponding lines obtained in the spectrum may be represented as shown in figure 3.25 on the next page. PKR branches in vibrational rotational spectra. In equation 12, omega naught represents the fundamental frequency. This is called center and the origin of the fundamental band. For change in quantum number is equal to minus 1, line with frequency lower than the fundamental frequency are obtained. This line is called P branch of the spectrum. For del J is equal to plus 1, lines with frequency greater than fundamental frequency are obtained, and these lines are called R branch of the spectrum. For del J is equal to 0, when a vibrational transition occurs without accompanied by rotational transition, del mu bar is equal to omega naught. Single lines should be obtained at the center. In actual practice, as the rotational constant of the two vibration levels are slightly different, a cluster of closely spaced lines appears at the center. This group of lines is called cow branch of the spectrum. When this type of transition is forbidden, in case of HCl, a gap appears at the center. Intensity of the lines in the P and R branch. It is important to note that intensity of the lines in the P and R branches of the type shown in figure 3.25b will be observed only if the resolving power of the spectrometer is very high. If the resolving power is not so high, then spectrum observed is shown in figure 3.26. Figure 3.25 show the vibrational rotational spectrum of a diatomic molecule. Figure 2 show the intensity of line of P branch, Q branch and R branch. Structural information from IR spectra. By carefully locating the band center corresponding to the transition V is equal to 0 to V dash is equal to 1. Fundamental transition. The transition V is equal to 0 to V dash is equal to 2. First overtone. The value of frequency omega E and anharmonicity constant Xc can be obtained. Also, the frequency separation between any two adjacent lines of the P branches and R branches gives the value of 2B. Knowing the value omega E and Xc, force constant and dissociation energy of the molecule can be calculated. Knowing the value of B, the moment of inertia and bond length of diatomic molecule can be calculated as explained below. Calculation of moment of inertia and bond length. As discussed in rotational spectra, B is equal to h upon 8 pi square IC. Frequency separation is equal to 2B, that is equal to h upon 4 pi square IC. Thus, knowing the frequency separation, moment of inertia and internuclear distance, that is bond length of the diatomic molecule, can be calculated. Second is calculation of force constant. Taking the simple case where a diatomic molecule may be considered as simple harmonic oscillator, an oscillator in which restoring force F is directly proportional to the displacement. According to Hooke's law, we have F is equal to minus kx, where k is the displacement and is equal to the distance to which the atoms has been stretched, r minus equilibrium distance between the atoms, that is equal to re. X is equal to r minus re. K in the equation 13 is called force constant. When x is equal to 1 cm, k is equal to minus f. Hence, force constant may be defined as restoring force per unit displacement of harmonic oscillator. It is found to be related to the equilibrium vibrational frequency omega E. According to the equation, omega is equal to 1 upon 2 pi under the root of k upon mu, where k is force constant, mu is the reduced mass of the system. To calculate k, equation 14, we can rewrite k is equal to 4 pi square omega E square mu. K is equal to 4 pi square omega square m1 upon m1 m2 upon m1 plus m2. m1 and m2 are the masses of oscillating atoms. Thus, knowing vibrational frequency omega e and the mass of the atoms of diatomic molecule, the force constant K can be calculated. Note that omega is in second inverse. However, a problem arises with the polyatomic molecule because each bond has a different force constant. This problem is solved by assuming a force constant is associated not only with the every bond but also with every bond angle. A detailed study of such molecule is beyond the scope of the present book. The force constant for number of bonds have been determined. It is found that force constant increases almost directly with the multiplicity of the bond. It is illustrated by some values given below. Bond force constant. If carbon have single bond, that is 4.6 then force constant value is 4.6 into 10 raised to power 5. If carbon and carbon atom has double bond, then force constant value is equal to 9.5 into 10 raised to power 5. If there is triple bond present between carbon and carbon atom, then force constant is equal to 15.8 into 10 raised to power 5. Thus, the multiplicity of the bond can be predicted from the value of force constant. For example, the force constant for C double bond is carbon monoxide is 18.6 into 10 raised to 5 Dan per centimeter, whereas the force constant for C double bond O in carbon dioxide is 15.2 into 10 raised to power minus 10 raised to power 5 Dan per centimeter. This result confirms that CO2 has resonating structure containing both carbon oxygen double bond and triple bond. So we can write as isotopic effect on the on the vibration and rotational spectrum. Taking the example of vibration rotation spectrum of HCl, it is found that if resolving power of the spectrometer is high, each individual line of the spectrum is found to be consist of doublet having a wavelength difference of about 27 angstrom. This splitting is due to presence of two isotopes of chlorine, which is chlorine 35, 37 chlorine in HCl. These isotopes with different masses result into different moment of inertia and fundamental frequency of vibrational omega e for HCl 35 and HCl 37. Hence, they producing splitting of lines. Vibrational frequency of different functional groups. The vibrational spectra of polyatomic molecule are very useful for the identification of organic compounds and for testing the purity of the compound by comparing its IR spectrum with that of pure compound. As already explained, a molecule made up of n atom has 3n-5 or 3n-6 normal mode of vibration. These vibration may be divided into two parts, that is skeletal vibration or group vibration. Skeletal vibration involve all the atoms of the molecule, whereas group vibration involve the vibration of small groups of atoms whose atom have more vigorous vibration than the rest of the atoms. The vibration takes place when the molecule absorbs energy in IR region. The energies thus absorbed are usually expressed in terms of wave number. It is observed that scatter vibration takes place when the absorption of energy is up to 15,000. Thus, they are characteristics of the molecules as a whole, that is, whether it is linear, branched, or has a benzonoid structure. This part of spectrum is called fingerprint region. However, certain groups of atoms or functional group, irrespective of the molecule in which they are present, absorb a particular wave number greater than 1500 centimeter to exhibit group vibration. A few functional groups show absorption in the fingerprint region. Thus, they give rise to characteristic absorption band in the spectra, by which we can easily predict that which functional group is present in this compound or the molecule. Thank you.